now it's no longer the case. So the big idea, for that, when Dr. Weaver and Dr. Rowe had spoken with two newbies like Greg McGee and me, was to try to start a series that we wanted to model it after, there's this thing called a tiny desk concert, where you have rock stars that are asked to come in, and they're used to playing the stadiums, and they come in and they just set their stuff up on a desk, and they talk about what gets them excited. And so we thought, man, we got a bunch of rock stars here, and why don't we get some of them to talk about what's making them excited. So I can't think of anyone more rock star-like than his truly over here. So Charles has had his ticket punched everywhere, like a lot of people here, but he trained at Big Blue in Ann Arbor for his undergrad. I was in chemical engineering, then off to Rice for biomedical engineering. Got your PhD, yeah? And then after that, you were at Yale, just like this one over here, for medical school. And he's been here ever since in neurosurgery, but there's no one that's thinking more kind of about helping people move through the world more and kind of human-machine hybrids right now.
You got a Yale coffee cup there.
Oh gosh, there's another, yeah, full of Yale. If you guys all sang, you could all be like the Whiffenpoofs. Yeah, Whiffen?
No, I was the outsider. I was the Big Ten guy.
Yeah, they look down their nose at you.
I know, right?
But anyway, so there's probably no one doing more thinking and doing on this stuff. A lot of people talk about it, but he's really doing it than Charles. So anyway, professor of neurosurgery, rock star, tiny desk concert for science. Please help me welcome Professor Charles Libb.
All right, Charles.
You're right. Welcome.
Well, thanks, David, for this. First, I really want to tell you that I had the opportunity to speak to lots of people, but this is really cool, because when I came as an intern in '96, Dr. Weaver, I think, was the director of the residency program, right? And he was.
I was.
Yeah, and he's like a fine. He's like a fine whiskey, right? I'm sure he's mellowed over time. I mean, really quite the force, as he continues to be. But no, it's really a pleasure, because in a lot of ways, as David mentioned, I've sort of, irrespective of how we've gotten here, right? We're all here. And, here in Southern California, we're part of this great university. We have amazing resources, not only on this campus, but also in UPC, and then all of the amazing institutions that, in particular in engineering, some of my collaborators at UC Irvine would always complain and say, if we were if we're not in Southern California, we would be the top-ranked engineering school in 33 states. But we're only ranked number 8 in Southern California, right? I mean, this just it's sobering, right, to think about the resources here. So we're all interested in lots of things. We're interested in the big term now is convergence. We're all interested in ways that we've become experts in looking at problems can converge into solving the problems of general interest to not only us but the world, right? And so we have lots of things in common. We're surgically minded, right? Which means that we understand that we want to make things better. We don't have to solve the problem in its entirety, but it has to be a immediate and very dramatic alteration of the course of the problem, and in a way that aligns very well philosophically with engineering, right? As an engineer, I don't care about the truth as much as I care about making it 15% better. So I'm principally interested in neurorestoration, which is the restoration function. This sort of thing is, it's we have lots of grants, but I don't take any money from anybody. Okay, I'm going to sell out someday, but not for something small. Okay. So I started out actually very interested in the cardiovascular system, right? And my PhD mentor is David Helms, who was the Dean of Engineering at Rice University, and he was one of the original engineers that worked with Michael Bacon on the Baylor Rice Artificial Heart program. So they never really built a heart, but the approach they took using computational fluid mechanics and essentially taking a very, what's more complicated? People underestimate the physics and the physiology of blood flow. When people reduce it down to, Are you kidding me, right? First of all, the system's completely reactive. It's not even, right? It's not even a Newtonian fluid, right? You're talking about particulate suspension. It's like a slurry. I mean, and everything, there's so much going on there that it is, in essence, one of the most complicated aspects of what keeps us alive. And so the research from that group ended up developing a focus on mechanobiology and biological shear stress that now everybody talks about in this. When you need to address the problem, you don't talk about mechanobiology. People almost look at you like, wonder why you're not, right? And so all of that work sort of started there. And so I became a neurosurgeon. I did my PhD and then I ended up going to medical school because, sort of realized that if we're going to solve the problems of medicine through engineering, you almost need to know what the problems are. It's impossible, right? For when we get consults from the doctors call us, right? And this is medicine, right? And they say, hey, you just fixed this problem. Like, you don't even know what you don't know, right? And so I went to medical school because I wanted to get more context on the problems we were trying to solve. So I wanted to use engineering to solve medical problems. I knew lots about engineering, didn't know anything about medicine, right? So I ended up going to medical school at Yale. Decade of the brain happened in the 90s, and I got sidetracked and went into neurosurgery. But what I realized was that we don't fix neurological function, right? The function of the nervous system is something that we don't fix. We don't even talk about fixing it, right? Because we were taught in medical school that function of the nervous system in adults cannot be reconstituted, can't repair, right? So everything's about prevention. And so, but whether or not regenerative medicine ends up stem cells and things like that end up ultimately having true value, what it did do was make us question that fundamental premise, right? Santiago Ramon y Cajal, right, is famous for saying that the adult nervous system doesn't regenerate, right? Whether he's, we know he's not right because there's all this evidence that he isn't right, but is he practically right? I don't know, right? I mean, if it takes that much research to find vestigial evidence of regeneration, right, is it going to be clinically meaningful? That's another question, right? But whether or not that fundamental approach to repair ends up being useful, it did get everybody at least thinking that it is possible to reconstitute the function of the nervous system, right? And so, we know that the spectrum of care goes, from the time people hit the hospital all the way to rehabilitation, right? And so I wanted to, in the next 25 minutes, quickly go over what our thoughts are about what it means, what neurorestoration actually means. People, when you go on the internet, I think Mike Capuzzo was one of the guys that talked about neurorestoration right from the very beginning, and he's wonderful. He coins, he's coined many important terms, right? And he was largely seen as an intellectual catalyst for the field of neurosurgery in large part of his career. But I don't think, and it's in no way to understate the importance of his contribution. Very often when people bring attention to a concept, the evolution and the maturation of that concept and what it ultimately comes to mean, right, can be very different. And so in the next 25 minutes or so, I want to really quickly run through what our thoughts are, because I think that if you look at the Neurorestoration Center, it was the first one that's been established in the world that I'm aware of, right? You now see neurorestoration centers being started up at Cleveland Clinic and at Methodist Hospital recently reached out to me to help consult on the creation of the neurorestoration center. So what is neurorestoration? It was amusing because as I talked through them, it was very clear that the concept of what constitutes neurorestoration in and of itself is not clear, right? And so in the last 10 years, in some respects, we've been central in crafting the identity of what this means. So there are, in our view, 4 principal pillars of what constitutes neurorestoration. Rather than giving fancy names and acronyms and so on and so forth, we'll make it really simple. Okay, the first one is repair. Second is replace. Third is optimize. And the last one is prevent. Those are the 4 pillars, right? So let's talk about repair. So repair was the original concept, right? Fetal tissue transplantation, repairing the nervous system, the stuff that went against the doctrine of Santiago Ramon y Cajal. So we have, looking out that window, you see this, beautiful buildings for regenerative medicine, right? And so there's a lot of work going on. There's a lot of what we call antegrade translational research, starting from petri dishes, going to animal models, going to non-human primates, going to humans. Can you believe that from where that started, from the original fetal tissue transplantation projects that were taking place in Sweden, right, that we still don't have a treatment based on stem cells?
Yeah, I can believe.
Yeah, right. Amazing. It's truly amazing. And and if you hang around long enough, you see ideas with all this promise, right? And then the balance of promise, it's always good to under promise, over deliver, right? Like, medicine always falls on the wrong side of that sort of calculus. Okay, and over time these ideas come back up again, right? So we have, in the last, I would say 3 years, there's been a renewed interest in stem cell transplantation, and I did my a lot of my sort of post my research as a when I tried to get back into engineering from middle of residency, and ended up over at Caltech with David Terrell, and who's now the provost there, right? And we're working on all these ideas of engineering the extracellular matrix to drive stem cell differentiation and so on and so forth, right? And so I gave up on that because I realized that cellular signaling was combinatorial, right? It's not an on-off switch, right? And but okay, so we kept our fingers on the pulse, and all of a sudden all these technologies appeared to be dragged across the regulatory and development process until there's something for us to look at, right? So there has been a series of, there were 3 clinical trials that are of consequence in the last few years, right? The one that has gotten a lot of attention here on this campus because of our involvement has been this one. This is related to the Asteris Biotherapeutics trial. This is a stem cell stem. When people say stem, right, it's quote unquote stem, right? It's a oligodendrocyte precursor cell that's injected into the cervical spinal cord of patients within 4 to 6 weeks after spinal cord injury in the subacute phase, right? And so the people listed on here are all the usual suspects in these types of trials, and I don't want to go into a lot of detail in terms of what the outcomes are, but it's not a controlled trial, small cohorts. What's interesting about this is that it looks at not just complete injured patients, it looks at incomplete injured patients too. So it may be, so when we crash our car, right, your ability to repair it depends on how badly it's damaged. So all of us believe that in the incomplete injured patients is where maybe the repair concept might have the most value. And I was very interested in this clinical trial because, number one, we are the state where California Institute of Regenerative Medicine was started because the feds didn't want to fund embryonic stem cell research. And so this is probably the best environment to do this kind of work, right? And this clinical trial was done in a partnership between CIRM and a private corporation, right? It's industrial academic sort of partnerships. And the guy that we injected, Chris Boson, was the first person in the state of California ever to get stem cells in the cervical spinal cord, right? So you guys know I'm really interested in cardiac, right? And I recently actually went down to University of Cape Town, Druid Church Hospital, and actually did a tour of the original, Chris Barnard sort of museum. And you look in there, and it's really sobering. It's like looking at the first rocket that went to the moon. You look at all the Falcon, heavy rockets are going up. They're so much more sophisticated, but the weight, the magnitude of that moment, right, of when that first happened, really should not be lost. And so it's not a controlled trial, but the problem with with subacute injuries is that there's still a chance for some natural recovery, right? And if it's not a controlled trial, it's very difficult to draw strict, rigorous conclusions. But the whole spinal cord injury universe is focused on this. And to the best controls that people have been able to get, which is historical controls with age and gender matched, sort of historical controls, it really looks like the signal's strong, right? And so there are 5 cohorts in the study. First, three patients were just, implanted with a very small amount of cells, just to see if it's safe and so on and so forth. And then the second cohort was the cohort that actually got injected with cells that were in large enough inoculum to feel like there would be a signal, right? And then it was incomplete, and then double the number of cells incompletes, and then double the number of cells incompletes. And so
what's the source of the cell?
these are, they're embryonic stem cells, but what's kind of cool is that, you remember the original fetal tissue transplantation where they literally took a lot of termination of pregnancy products and took lots of them, put together one inoculum for one patient, okay? That's called non-scalable, that's a non-starter. This is colon-genically expanded cells, right? And every single patient in this clinical trial were transplanted with the same source. So it's lots of patients from one source, and I don't know the exact way these cells are procured, but my understanding is that it comes from fertility clinics where the embryos, I suppose, that frozen are not going to be transplanted or then used, otherwise tossed, right? So very, very good point. Okay, so I'm not going to go through a lot of that, and I think that you guys, I'm here, so if any of you are interested, I'll take you on a tour of the stuff and actually get you to meet some of these patients. But what's kind of cool is that now my goal in life is to go dark, okay? Because we don't want to be out there, okay? This kind of stuff is never good for doctors to be out there. But I think that at some point, I started to become less resistant to speaking to the general sort of press, because I think that if you look at all of these things we're trying to solve, all I know is we've got something the size of Mini Cooper driving around on Mars, right? We've got something the size of a World War II submarine driving around the ice cap at the North Pole, okay? And that's an engineering problem too, right? So whether or not we ultimately solve this through an engineering problem requires that there's public support for this sort of stuff, right? And the public has to see this as something important. And so this sort of stuff is you don't ever want to drive it, but you definitely need to participate and help it along, okay? And so, so the Nature Outlook, you guys know the magazine for Nature, and I came across this at an airport, and so this generated quite a lot of visibility. Second concept is this concept of replace, right? So we talk about repair, and so what about replace? So the body, the brain, interacts with the external environment through the body. If there's a disconnection between the brain and the body, then the brain can no longer interact with the external environment, right? It's molecule separate, for example. Can there be a direct interface that's created between the brain and the external environment? I mean, philosophically, one can wonder what the implications of that might be, right? Elon Musk and others, have been talking about how augmentation of human intelligence is the only way that human intelligence has a chance against AI, right? And so, okay, now we're getting way, way ahead of our skis, right? Remember, I'm perfectly comfortable with the idea that the healthy human being, right, is as close to perfection as we're ever going to get. Okay, so now try to reconstitute any simple aspect of neurological function is really hard. Okay, so what are the things that need to happen? So we started a collaboration with Richard Anderson. You guys might know Brian Lee. Brian Lee he actually was a PhD in the Anderson lab. He was an MD PhD student here at USC, and I met him when I was at Caltech during my sort of wanderings over there, and I talked him into becoming a neurosurgeon because we were both USC football fans, and we take care of the football team, and I'm sitting there, and this is when they didn't require that the neurosurgeons travel with the football team before the whole head injury stuff, right? We used to be able to just go to the home games, and then if we wanted to travel, we could travel. Now it's like they require us, right? So we were sitting there. I was at, I think, Carmine's restaurant, right in Pasadena, right by the freeway. And here's another guy sitting there rooting for we were playing the, I think, Oregon State Beavers. And we started chatting, and he turns out he's a PhD student at Virginia. I says, well, what are you doing? He goes, well, I'm doing brain-computer interface research. I said, what is brain-computer interface? I don't know what that is. He goes, oh, neuroprosthetics, computational neuroscience, recording from the brain, decoding those recordings. We know that the function of the brain and information encoding and transmission is in fact found in these, dynamic electromagnetic oscillations that occur, right, as the ensemble effects of millions of neurons firing, right? I said, okay, well, I don't know what that is, but you gotta be a neurosurgeon, because if you ever wanna see this in a human, right, there's only one kind of doctor that can touch a human brain without going to jail. Okay, that would be a neurosurgeon, right? So several years later, he calls me and he goes, hey, I wanna be a neurosurgeon, right? And I said, okay, I guess we have to get you in the residency program, right? This is where I think that we have to be a little bit kind looking at specific credentials, because, Brian's board scores weren't as high, right, as they could have been, but we got him in. So Richard I can't overstate his role in BCI. When we go to the brain-computer interface conferences, I think virtually every single important person there was his postdoc, right? He's sort of the father of BCI, right? And he's been working in non-human primates for years and years and years, and looking at different parts of the brain, understanding that the brain doesn't work the way neurosurgeons think it works, which is this part of the brain does this. That is not how the brain works. The brain is a fully integrated, highly orchestrated, synchronized function of all parts of the brain working at once, right? And so Richard is famous for, amongst other things, right, understanding what features of any kind of brain function can be extracted from different parts of the brain, right? So working the parietal cortex to look at goals and intentions rather than direct motor control. Like, the idea that I do something for one goal versus another goal, the motor part of it can be the same, but the goals could be completely different, right? So we started this project. Again, I'm gonna go through them very quickly, and the idea is to put in, look for intense signals in the posterior parietal cortex, putting in high density microelectrode arrays, right? And having the behaving patient be the context through which these signals can be interpreted, right? And so we basically implanted these MEAs, and this is the first time this part of the brain had been implanted. What's really cool about the first ever is that you go to the moon, right? Every rock you pick up is never been seen before. It's awesome, okay? And so this is Eric Sordo. He's our first patient. He's probably the most famous person at Rancho right now. And he's got these two arrays. You can see they're permanently implanted. He's coming up to the end of 5 years. This was meant to be a 1-year project, right? And this was initially funded by DARPA, and then DARPA is painful for any of you guys who, it can't be painful.
That was a PTO?
Yeah, and so we ended up funding this ourselves internally for a little while until we got NIH Brain Initiative grants and so on and so forth that ultimately funded it. And this is our lab, brain machine interface lab at Rancho, and you guys watch Grey's Anatomy, right? There was a episode that was this, and they came and filmed everything, and Dr. McDreamy was sort of involved in punching these arrays into the brain. Yeah. And so this is what it kind of looks like. So you got 100 microwires. They're very tiny, and they're embedded in the brain. And every time a patient does something, a task, the individual neurons, the spikes are recorded, and the features and the combinatorial features. Remember, it's not just one spike, right? It's the combined features of multiple. It gives you a pretty rich sort of signal, right? And so we have, again, I don't want to go into a lot of detail with this sort of stuff, but the advantage of the parietal cortex is that the processing speed is really fast, and it's bilateral, right? Like when we hit a golf ball, Fred, right? It's not just, right, when we try to hit a golf ball, it's not just the left side, it's the left and right achieving one goal, right? And so that one goal is encoded in the parietal cortex. So the processing speed is really fast. And I don't know if this is going to work, but if it may not.
So he's a
C4 quad. He's been shot.
C4 quad.
Yeah, he's been shot in the neck.
No way.
Yeah, so he's using his thoughts to
So he's using his thoughts to direct that.
yes.
Is that a soda or a beer?
It's a beer. It's a Modelo. Yeah. So this guy, we did this right
Oh
before.
God.
That's so cool.
Oh, yes.
We had to embargo this because Science, it was published in Science, right? And Science didn't want us to announce it after they published it, right? And
So Charles,
Yeah.
the things on the top of his head, are those like?
Yeah,
No, I understand, but are those, so when he leaves this thing, do those things? what do
Yeah,
you
they
mean?
unscrew the great part, and he has 2 horns.
Oh.
Yeah.
And
it's
so
like
he hasn't had
Matrix.
any infections or anything?
No, amazing. When I first, Fred, that's the first thing I thought. I was like having nightmares of CSF leaks and all that, right?
So that's all based on
Yeah.
intention trip mapping?
Huh?
That was based on intention mapping?
Yeah, yeah. So Eric, we were embargoed, right? But it came out. We've got actually a really great media relations department. They sort of it came out right around Memorial Day, and this made the top 10 lists of ways to have a cold beer.
Well, was this the one that was in the Wall Street Journal?
Yeah. This was in every language, and it was kind of cool because this was the first time. I mean, people have looked for BCI approaches, but they've all implanted motor cortex.
Right.
So motor cortex is at the level of like a captain in the army, right? You don't see the higher level strategic goals. It's like, okay, take the hill, good. But why? You don't necessarily know that, right? I mean, some general up there is managing the overall picture, and so trying to extract information at that level is what the major advance has been. It's at a higher cognitive area. So I want to show you that, that when you extract information from the brain, there's lots of different levels of resolution. There's levels of the single unit, which is what we're doing on the other study, right, with the microarrays. When Eric sort of thinks, we're recording single neuronal spikes. So I love football, so you take a look at a football stadium. If you sit on the blimp, you look down, you get one field of view, and you get one set of information, right? If you sit in the home section, you get another set of information. If you talk to one individual person, like, right, head coach, starting quarterback, you get a different set of information. Information's different and specific, and it may be the multi-scale information that gives you the complete picture, right? So we can record from the brain at the single neuron level. We can record from millions of neurons, average, it's called local field potentials, right? And we can also record at the level of millions and millions of neurons through a, multiple square millimeter section of brain, and that's called electrocorticography. So we have the ability to record at all of these different levels, and it may be that the recordings at one level can achieve a certain kind of control, and recordings at a different level can achieve another set of control. Okay, what do I mean by that? You know how like in church, pastor goes, stand, and the guy stands, right? And everybody goes, okay, that's easy. I could put functional electrostimulations and contract the muscles and get somebody to stand, right? It may have nothing to do with the brain. That's actually not hard. This is hard. Okay, so this is why we look at the amount of brain in the hand area is huge. The face area is huge. The leg area, it's tiny, right? It's in the interhemispheric fissure, right? So when we walk, what is the neural process for it? Well, it's sort of a shared controller, right? Because a lot of the central pattern generators are actually in the spinal cord. So the brain basically says start, stop, how fast, okay? So start, stop, how fast may be decodable from electrocorticography, right? You may not need single units to decode that. So we put together a series of studies with a group initially at UC Irvine, because these are the engineers that are able to do, that, we're friends, right? Say, hey, why don't we do this? So we started some sort of unfunded, self-funded projects over at Rancho Los Amigos, right? And we put these electrodes in our epilepsy patients, and we got these epilepsy patients to get up, get on a treadmill, walk around, and we wanted to see at the electrocorticography level whether or not we can decode the signals with some sort of specificity for walking. We found that we could, right? So, so this is kind of what it looks like. We can see the power in the high gamma band increases when you walk, and that's modulated by walking speed, right? So it's kind of what an animation looks like, right? And Because that's the only reason, you know, there are rules against human subjects research. You can't experiment in humans, right? So what's really great about our clinical practice is that they're getting this anyways, right? There's no cost and no additional risk, right? So for example, the Eric Sordo project, there was a lot of money just to take him to surgery. We all know that, right? Okay. And so the experimental part is actually something that, you know, you can do over a long period of time, right? Whereas this, these patients are getting electrodes in, we're looking for seizure foci, we're curing their seizures, right? And so if they're sitting in the EMU and they do some tasks while they're waiting to have a seizure, what's wrong with that, right? There's no ethics consideration, nothing. Okay. So, you know, and this is for some of the younger folks, right, here. You start out by having an idea, right? Then you test it out, and then you got to get a grant. A grant is like a child in a marriage. You know, it brings together collaborators. You have to get a grant, even if it's a small grant, because one really cool thing about grants is it gets renewed, right? And it forces you to be successful, right? And so we started out with self-funded, very small grants, and then we got $1 million from the National Science Foundation, which, you know, it's a big grant for NSF, right? NSF grants are small. And just last year, we were awarded a $8 million Cyber Physical Systems Frontier Award, which is the biggest grant NSF gives, right? And this is, you know, so you can see that the people that were involved are the UCI people, right? Where we were working with them separately, and then the Caltech people who were doing the artificial sensation, we were doing that separately. So 3 years ago, I said, you know, we should just get we should get this band and this band together and go for something big, right? And it's for us as a clinician, we don't really need credit for these types of things. We really don't, because we have a day job. We can operate, right? And the research funds will never pay you what you feel like you need to be making, right? So I don't ever arm wrestle with anybody for PI. You know, it doesn't matter, right? You know, when you look at the entire spectrum of projects, it becomes very clear that you know, the involvement is, and ultimately we're clinicians. We're aimed at fixing the problem, not, you know, getting a grant to solve one particular aspect of the problem. And so, you know, again, you know, got this lady up walking. She's wearing a robot exoskeleton, right? She's paralyzed from the waist down, and yeah. So this was kind of cool.
So how does that
Okay,
work?
so this robot is not under brain control. Right now, this robot is just a wearable robot. It's like any one of the robots that David and I play with.
All right, so you just put her in and then you turn the robot on.
Right. What we want to do.
That's like it's like a microphone.
Yeah.
It's like
Right.
a mic, right? It amplifies your intention to move.
But what we want to do, the real project is to put arrays in the brain
Yeah.
to use the thoughts to
Connect
drive the
the
robot.
robot.
But not only that, there's sensors on the robot that apply stimulation to the S1 cortex, so the patient can actually feel, right?
Sensory substitution.
Yeah.
So how much of that would you rely on external programming for the robot itself?
Oh, it's great because it's a shared controller, right?
Yeah.
The spinal cord does the gate anyway, so
Yeah.
that's just natural, you know. So the key with BCI is how much information do you actually need to achieve you know, to recapitulate. Look, God had one set of rules when he invented us, right? Okay, and so, you know, unless you can control every one of those things, you're not going to recapitulate that. So this is the modular engineering approach, right? The deconstruction, reconstruction, putting it together makes sense. So I want to just spend a few minutes to talk about optimization, right? Optimization is, you know, it's not fair to say that doctors haven't cared about function as a primary goal of treatment. Rehabilitation doctors have, in fact, cared about that, right? But rehabilitation has really been driven from the orthopedic side. I mean, USC again, Jack and Perry, right? All of this stuff, it's been this, and this is why our PT department is ranked #1 in the country, right? But what they didn't focus on was the brain aspect of it. Like if I have a stroke, they work with my arm because it doesn't work, right? But the problem is here. Okay, so looking at the brain aspects of it. Now, moving forward, we're layering on this concept of neuromodulation, right? Stimulating the brain, modulating the brain, in conjunction with task-specific practice to make it work, right? So again, I just want to give you one example of a clinical trial that we're involved with So what I do is I look at these things. These are concepts I think very important. I look around. I can't spend my whole life inventing a technology, so I bring in technologies that represent an expression of that concept, and I try to see within the context of my clinical practice whether or not there's value to it and how it really fits, right? So this is the niche trial. So stroke rehabilitation, but using navigated transcranial magnetic stimulation to inhibit the contralateral hemisphere, right? And this is kind of what it looks like, and this is ongoing at Ranch. And we just actually finished up the follow-up study to it because the original study showed that rehab really worked well, and there was some question whether or not the sham coil didn't also give treatment, right? So I'm not going to go through this a lot.
So how do you signal to the brain?
You use okay. So neurosurgeons, all of us think that the currency for brain communication is electrical, right? Because a neuron fires electrical potential. But we all know that when you have a current, you have a magnetic field, and you spin a magnet, you generate current. So they're actually corollary, right? The problem with electrical potentials, the skull is like it filters everything out. It attenuates, right? That's why you want to put electrodes in the brain.
Right.
But magnetic potentials can go right through the skull. It's like it's not even there, right? So if you can alter the magnetic potentials that the neurons experience, you can alter their behavior. Okay, so this is where the sham coil, unclear. Anyways, bottom line is that a lot of people are looking at this, right? There's implantable technology. I always get this, right? Oh, you're a surgeon, right? They're gonna do all this stuff, and you're done. I'm like, no. Surgery. I see surgery as the physics of the problem, right? All the doctors giving medicines, you're the chemists, right? You're leveraging the neurochemical properties of the brain. Okay, we fix everything physically, right? And I mean, sticking a screw in a spine or clipping an aneurysm, that's physics. Sewing a hole in an artery, that's physics, right? Taking out a tumor, that's physics. But there's all kinds of cool kinds of physics, right? That is very much within the scope of neurosurgery. So implantables also have value, right? Because if you want to set it and forget it and just have it go, right, then you want to implant it, right? So this is another clinical trial that there was just another press release because we're the first people to implant one of these things in the United States, where it's again a stimulator. The vagus nerve is the principal parasympathetic output from the brain, right? And the cervical trunk of the vagus nerve is like an antenna to the brain. So we can put stimulated coils around the vagus nerve. We do this for epilepsy already. Now we're doing this for stroke rehabilitation.
So how does that work in stroke rehabilitation?
So the idea is when you stimulate the brain, there's several things, like to make me learn better. I can give me information better. That's a code that I'm learning, right? I can also rouse me so that whatever code's coming. So I'm not getting the specific code, but the awaking, right, of being called to attention. So when you unrouse, right, you come in, you pound everybody, and everybody snaps to attention, and they learn better. Period, right? If they're just slouching, they're not gonna learn. Okay, so it's not the specific code that you're giving them; it's the waking up kind of thing, right? So we're not. This is probably more the waking up,
So
right?
Stimulating the vagus nerve wakes them up.
Well, primes the system so that the rehabilitation. That's the idea. That's the hypothesis, right?
Interesting.
Yeah. So I want to give you another example, and I only put this in because Dave and I have been talking about physical therapy and biokinesiology, right? So Jim Gordon recently appointed me to his department, and because we're working on it, because I think that the brain modulation part is important, but the rehab part is important too. And so we started to, do you guys know that with Parkinson's now, the whole paradigm shifted to exercise, right? And a lot of that work was done here. Beth Fisher was the first person to publish this in humans, right? And so we started working with Beth. So if rehab is better, then the combined contextualized cognitive and motor rehabilitation is probably even better, right? And so this is work done in experimental psychology all over the place, and so I'm not going to go through this. You guys can come and watch the studies. Please come, please call me, and I will take you by and we'll watch these studies. But it's based on this. Pardon me. Ooh, what happened?
What happened?
Crashed.
Recover, man.
just, there we go, yeah. Sorry, pardon me, I don't know what happened.
Or you can probably scroll down to
Yeah,
where you
scroll
want.
down to the word.
Oh,
Here it is.
oh, you can do that too.
Oh, fatal error.
Whoa.
Okay, here we go. Let me just scroll down to this one slide, and then I want to finish because it's, let's see, yeah, this. Okay, so this is simple, right? And what's wonderful about the simple, you know, it's what it really represents is amazing. So the inventor of this technology is Kathy Lamperti. She's a South African gal, and this is a device where each module is actually a LED matrix. And using assembly language, you can coordinate all of this. This is exactly the same way. You guys go to China and you see the entire city and you see flocks of geese flying across the entire city and that kind of thing, right? Same kind of concept, except that you can make it so that patients actually interact with this device with different levels of cognitive load. One asymptotic place would be pure visual reaction time. Anytime you see a light, touch it, right? You do all this, right? If you just add, only touch it when you see a smiley face, or only touch it when you see one color, the cognitive load is increased, right? It's like, and then you can make it so that people do square roots, you know, subtract by 3. I mean, you can make it so that the cognitive load while they're doing the exercise becomes adjustable in infinite sort of ranges, right? So why is this important? Think about rehabilitation now. So I'm director of neurorecovery programs at Rancho, right? So one of the things I want to do is change rehab. What is rehab now? Is PT, OT, speech, inpatient, outpatient, and then nothing. That makes no sense to me, right? So what if we were able to use something like this in the inpatient setting, and then they go to the outpatient setting, right? And then you put one in the wellness center or the local gym, right? And
Or
they
their-
can
or their
continue-
home.
Or their home, right? They
Or
can
their
continue.
phone.
Exactly, they can, and, you know, the phone, the apps, right? How they perform, the therapist can literally sit there and go, well, okay, so Dr. Liu, you're doing okay here, but I think that if we did this, and they program for you, go up there, you boom, you load that up onto the device, and and so it would be a way to completely transform it, right? Okay, so layered upon the rehab, remember, optimization is brain modulation plus task-specific practice, right? So I've just shown you an example of clinical trials with stroke rehab, non-invasive, and then invasive vagus nerve, right? And now shown you an example of a device that brings to physical expression the concept of simultaneous, contextualized, cognitive and motor rehabilitation, right? So how are we gonna hack the brain modulation piece, right? So I'm working with, I've just brought in three scientists into our neurorestoration center that are looking at using transcranial magnetic stimulation, not just for exciting or inhibiting, like 10 hertz excitatory, 1 hertz inhibitory. No, how can we use this to actually modulate? And so this is based on EEG recordings, and you know, we use quantitative EEG. This type of work is actually in the realm of experimental psychology and psychiatry, right? And so we brought that in, and this is actually my brain. And if you look at the concepts that are driving this, I mean, okay, so this is Georgi Bushaki. He's director of the Brain Research Laboratory at NYU right now. He's one of the most eminent people looking at the rhythms of the brain, because it's not just the neuron firing or not firing, it's the synchronized rhythms, right, that occur in the electromagnetic potentials of the brain, where the information is coded and transmitted. And Christoph Koch was over at Caltech, right? He was actually on Brian Lee's thesis committee, and he's up at the Allen Institute now. And these guys were all saying that it is this ensemble effect that we need to study. So we're doctors, right? You know what we have? We have context. We have the behaving patient. Those guys have nothing, right? Each one of our patients is a Rosetta Stone. People are generating reams of data that they can't interpret, right? And so a few contextualized Rosetta Stone style data sets will allow us to potentially interpret all of that. So this is the tune the brain concept, right? So I just want to neural restoration, use synthesis, repair, replace, optimize. This last piece, which is prevent, that I haven't fully developed in my mind yet. But this is the part that I want to work with you guys on, right? Because I think that the fundamental reason that pathologies are generated that we care about, right, which is peripheral vascular disease, cardiovascular disease, and diabetic foot, et cetera, is also the same reason we get all these strokes and all these things, right? And so I think that together we need to drill down to that. And I know that there's always two aspects of every problem. It's the brain and the body, right? So I'm not sure that anybody's looking at the brain and its role in all of these.
I don't think anybody's looking at that,
So,
that I'm aware of.
Right.
A lot of chemistry,
Yeah.
statins.
right, so we are gonna start looking at that, right? And so, we're gonna broaden definition of neurosurgery. We already talked about this is the brain and, can't do this alone, obviously. Right? And so, we've been able to pull all this stuff together, and I think, one thing I'm really delighted about is that the university actually made a pretty modest investment in us and to create the Neurorestoration Center, right? It was really to keep me here, because I was gonna go to the University of Washington, do a big job. And I ended up staying in LA, and it was one of the best decisions I made, right? Because LA is an incredibly highly resourced part of the world. There's only two things that have generated wealth in the last 30 years, right? One is digital age revolution, right? West Coast phenomenon, and then the rise of China and Asia, which is also a West Coast phenomenon, right? So it's been really, really productive for us, we've been pretty creative in terms of aligning goals and getting all the scientists and so on, right? Make them successful, give them opportunities to work with us in the context of clinical patients, right? I think we probably play a small role in Rancho's emergence again, right? In the value of that, right? For our ecosystem in a way. And I've also taken some lessons from David. David has been instrumental in creating these systems level fixes for the things that he cares about, right? And so we've done that too, right? So we've just created the USC Epilepsy Consortium. The epilepsy is wonderful because, as you aptly pointed out, why epilepsy patients? Absolutely, that's the only time I can actually put electrodes in people's heads, right? And not cost a lot of money and not go through ethics committees and so on and so forth, right? It is a wonderful way to go. But anybody here taken like human subjects research, you can't take and not give back, right? That's the fundamental thing. So if we're gonna give back, how do we give back? Well, we cure more people with epilepsy, right? And so we've actually created, since I've been here, 4 National Associate Epilepsy Centers in Southern California, right? We created one here, went down to DHS Rancho, created one there, right? It's the only one for underserved populations ever. Went down to Hogue, created an epilepsy center at Hogue, and then we just established one up in the Central Valley. It's the only one in the entire central part of California. And so that's, I think, modeled in a very similar way after some of the systems level integration concepts of what you guys are trying to achieve there. So I see tons of synergy. We care about the same problems. We know that the fundamental issues that are generating pathology on our side that we're having trouble fixing, right, are the same, right? And so, it would be really wonderful if we could sort of, circle around and think about ways to the good thing about peripheral vasculature is the same thing happens in the brain, except that this is kind of painful to get to, right? And the numbers of opportunities you get to get there and take samples and pieces of it, right, is like 0. You can't take a segment of the MCA out, okay? That's not gonna happen, right? But can there be ways that once we figure this out, right, that we can use the opportunities outside the body that are just, again, happening as a matter of general medical practice, right, to see the effects of some of these things that we're doing. Like if we fix the brain, we do something to interact with the brain, I would bet that if the arteries in the brain are getting better, the ones outside are getting better too, right? And it's a lot easier to keep track of those than the ones in the brain. So these are just a very immediate, obvious way for us to connect. Okay.
Thank you.
Too long.
Very good.
Yeah, I was nervous. This guy, man, I'm telling you, I was his intern. I was his intern, let me tell you.
Well, Professor Liu,